Hello.
Good morning. How are you today? You're mute.
Good. I'm still eating my breakfast though, just finishing it, but we're all good.
Great. Good to hear that.
Oh,
You did-
I just wanted to mention that the reason I'm always like running in last minute to lab class is because my other class that I have after this ends literally 10 minutes before lab.
Okay.
So that's why I'm always like the last person there, is just because like I don't have time. And especially if the class runs late or anything, I'm just like sprinting down the hallway.
Oh, okay. I understand.
All right.
All right. Did you see the lab materials I uploaded?
Yeah, I printed off this one.
Yeah, you need that.
So, and then I'll have my laptop with me too. So
Okay. So every other information is downloaded into your laptop.
yeah, I think so.
Okay. That's great. Okay. Hello, everyone. I hope you all saw the announcement about the lab. And we've seen the materials as well. Okay. All right. In the lab, we'll have the discussion of how we'll be running the lab for these next 2 weeks. Okay. Okay. So in the lab class, we'll discuss when would be the best time to have a midterm. I'm proposing after the Thanksgiving, but I'll finalize that by the end of the lab class, okay? And I'll announce to us when that'll come up. But it's going to be in 2 weeks' time, or not less than 2 weeks' time anyway. Okay. So last class, we looked at forces. We introduced the lecture for chapter 4 that is talking about forces and then Newton laws of motion. We introduced the second part of our discourse in describing motion, that is describing motion in terms of each representation and considering the force as well. We've looked at the representation in the first 3 chapters, and then we're advancing into looking at the forces causing the motion. And we looked at the basic or common sense definition of force to be the force of push and pull. We looked at the different properties of force that applies. We also lastly looked at catalog of forces that we'll be interacting with in this course, okay, that we'll be discussing. And we'll have about, I think, yeah, about 8 of them, which we should easily remember or recall. Just get an acronym to recall them, because when you know them, it will help you to solving problems or identifying forces that are present when an action is being taken. Okay. As a reminder, I have a table of the catalog of forces that we discussed in the last class, which will show after this, the slide we are looking at now. So we're looking at how we identify forces when we see an action on an object. Okay. It will be of good interest to identify all the forces that is acting on the object, because that will help us process perfectly the net force. Net force, which is like the resultant force. Because we know that force is a vector, we know it's going to take the same model or pattern like analyzing all vectors, okay? Just the only difference is in the constituent of what force is, okay? Just like we know that acceleration is different from velocity, but we know they are all vectors in terms that we can define them with their magnitude and their direction, okay? So it is necessary to determine all forces acting on an object to process correctly or accurately the net force. And also, it is important as well not to add the force that we think is existing, that is adding forces from our imagination. And that is why it is important to have the knowledge of the catalog of forces that we discussed in the last class, knowing how they come into play and how to describe them in terms of direction. And we looked at some characteristics of those kind of forces. It is this knowledge that defines or that helped us shape the step-by-step process of identifying forces, okay? So the step-by-step processes is what we have put into the tactics box of tactics 4.2. Okay, so before we solve problems relating to forces, that is identifying the several forces that will be acting on an object, we have to follow these basic steps to identify the forces, to prevent adding or avoid adding, including forces that do not exist in the motion experience. So the first is, whenever we have an object being acted upon by a force, the first thing to do is to identify the object of interest. So this is the object whose motion we wish to study. So we'll make or draw a picture of the situation. That is, show the object of interest and all other objects around the object of interest, such as the rope, the spring, the surface, the contacts, or influence of any other thing we can identify in that action, okay? So having identified the object of interest, and you draw or make a picture of the situation, that is, try to represent the situation in a diagrammatic form, we draw a closed curve around the object. Okay, so the next thing will be to make a closed curve around the object, that is, circle the region or object of interest. Only the object of interest inside the curve. Don't add any other thing inside that curve or that circle you're making. Every other thing will be outside, because they will help you to define the point of contact around the object of interest. And then you proceed to locate every point on the boundary of the curve. Okay, locate every point of the boundary of the curve. where the other object touches the object of interest. That is, we are emphasizing contact forces. Locate every point around the object of interest where you can say there's a contact force. You know what we mean by contact force. We saw that in our last class. Force, that is force acting on an object that has physical contact with that object. Remember, we'll have the contact force and the long range force. Okay, so making that circle will help you pinpoint the contact forces around that object. So the next will be to name and label each contact force acting on that object. You should be able to name, label the contact forces acting on that object from the understanding of the catalog of force. You already know. For example, if the object is tied to a rope, you already know that the kind of contact force there is called tension, because the force on the rope is called tension. So you name the kind of contact force that is around that object. Okay, so you can either write it out or use the symbol that we've already learned in our last class. Each force has their own symbol. So once we see the symbol, we already know what you mean. So the last will be to identify the long range force acting on the object. The most common long range force is the weight, which is subject to gravitational pull on the object. Okay, so these are the 6 basic steps that we should keep at our fingertips to identifying forces. Now let's see how this applies in everyday life. So we'll take this conceptual example of a buggy jumper. So a buggy jumper has leaped off a bridge and is nearly the bottom of a fall. What forces are being exerted on the buggy jumper? This is the artistic version. That is like the picture of the buggy jumper. We see it has lifted off the bridge, almost at the end or bottom of his fall. What did we say? We identify the object of interest. The object of interest in this case is the buggy jumper. We made a picture diagram. Now this is the artistic version. Let's look at what a student sketch would do if this is the kind of question you were asked to do. This is your sketch of the buggy jumper. Buggy jumpers always have rope keeping them from falling off totally when they are making their jump. So this rope keeps them in place. So we identify the object as the buggy jumper, which we made the picture of the human. Then we drew a circle around the object of interest. Okay, that's this circle. So the next the next step, that is step 4, is to locate the point where other object touched the object of interest. So we see the rope touching the leg, tied to the leg of the buggy jumper. We made the sketch of that rope and we labeled it. We labeled the contact force identified. Okay, so the contact force identified in this case is called tension. And we put the symbol of tension with the arrow showing that it's a vector. Okay, so the next, which is the 6th step, the last step is to determine the 2 types of forces, whether they are contact force or long range force. Okay, so we have identified the contact force to be tension, and we identified the long range force because this object is suspended in the air. if anything happens to that rope, it's going to go all the way down because of the gravitational pull on this object, which is the weight. Okay, and weight is the only long-range force acting on this object. So we see that with this understanding, we can actually identify forces that are acting on objects, which inform the experiment we'll be performing in class today, and then identifying the different forces that will be acting on the object we'll be looking at. So we'll talk more about that in our lab class. So let's take the second example.
I have a question.
Okay.
I was just wondering with like the weight, could you, if you wrote like FG, like force due to gravity, would that be incorrect or would that be okay too?
Okay, you're asking if we write force like that?
Yeah, like instead of weight, because like, yeah.
Yes, you define, as long as you define it, you define this to mean, but anytime you're talking about weight, it has this symbol, okay? So if you said weight has already been defined as the force due to gravity or force under gravitational pull, okay? So we can always say force, tension force. You get it? So we can always define this, but when we are referring to weight on its own, we have to write it out with the symbol, having the understanding that it's a kind of force that is subject to gravitational pull. Okay. Okay. So you can always put that.
As well.
Okay, I'm listening.
Regarding today's lab, is there a lab report due or just that sheet that we filled out last week?
Yes, the lab is a long one that will have to do within 2 weeks. Okay, there'll be lab reports every time you do lab.
So is there any lab report due today?
From the last lab report is due in the next lab. Always due by the next lab.
So yes, there is a lab report due today.
Okay, yes.
Okay.
All right. Okay, so I'm expecting that as you're coming into the lab, you are handing in your report as well, okay? So let's take the second example. It's a conceptual example as well about a skier that is being towed up a snow-covered hill by a tow rope. We can see the tow rope. And we know something about tension force is always the force acting on ropes, okay? So whenever we see rope, we know, oh, there's tension force present, and it's the contact force that is readily present when there is rope, okay? So a skier is being towed up a snow-covered hill by a tow rope. What forces are being exerted on the skier? We use the same 6-step, identify the object of interest, which we did. It's a skier, that's the object of interest. This is the artistic picture. So let's look at what you would draw, which does not have to be perfect. So you identify the human, which is the object of interest. You made a circle around the object of interest. Now this circle helps you, this circle is helping you to define or see clearly the contact forces, okay? You identify the object of interest, made a picture of the situation, then you drew the curve around the object. The next is to locate the point where other objects have contact with that force. So we can see one contact here, and we can see another one here. All right. So we have the tension, the normal, you can see the normal force, and the kinetic frictional force, because it is being towed up, it's in motion. So it will have friction And then it has the normal because it's standing. So it's exerting weight on the surface. Then we have also weight, which is the force due to gravity that pulls that object towards the earth. So the contact forces have been identified, labeled, and the long range force as well. Weight is the only one present in this case. So we have several examples which will be looking at the description in the assignment that I'll be giving to you on Friday to describe some of the conceptual, some ways or give some ways to identify forces on objects, forces, several forces acting on objects following this basic step. Okay, so we'll have the example 3 to buttress the point on identifying forces. So by now we already know exactly how to do that following the steps. Identify objects, make a picture of what you can describe from the text given to you, draw your circle around the object, identify points of contact, label every contact force, also identify the long range force and label them as well. So the last example in this, under this is the example of the rocket that is flying upward through the air. A rocket is flying upward through the air, high above the ground. Air resistance is negligible. Remember we said that unless otherwise specified, everything we'll be doing will be such that we'll be neglecting air resistance, okay? But we factor air resistance when we have to specifically deal with the force called drag, because drag is typically the force due to air resistance, okay? So in this case, air resistance is negligible. And the question is, what are the forces? What forces are being exerted on the rocket? So we see the rocket take off. We'll have the thrust, that is force of thrust. We'll have also the influence of gravitational pull, which is a weight. And then we'll have the drag, because it's going to be bumping into the air. So we'll have the drag, it's going to experience that first drag force. In this case, we see that the object is in air. When an object is in air, mostly we have the long range force of weight acting on it. Even when object is on a contact surface, like we see in the normal forces, we also have the long range force of weight acting on that object. So we used our method, identify the object of interest, which is the rocket, made a picture of it. It is going upward into the air. We circled the object of interest. We identified contact force, the thrust, which is the force coming from the gas of the rocket, the resistance that it's going to face, which is drag force, then the weight, the force that tends to pull it down back to the earth. Okay.
Wait, so is drag also a contact force?
Yes, drag is a contact force. We established that
Okay.
in our last class.
All right, I just wanted to double check. Thanks.
You're welcome. We typically have drag, you know, when you are in the wind, you might not feel the presence of the wind like tied like a rope, okay? But you are having contact with that. It's not like the weights that tend to pull the object to yourself, like weight, magnetism, electricity, they're different. Okay, so we had two contact forces here and then the weights. Okay, so let's take this before we go to the next one. Okay, you have kicked the rock and it is now sliding across the ground about 2 meters in front of you. Which of all these forces that we've listed in the option is acting on the rock? You're going to have more than one answer. So it's not just one option. So that's why we said include all that apply. Okay. So if we look at using the description of the steps we have already learned, we'll be able to see from the options a statement that really does not apply, because we have some statements that, yes, in terms of the description of forces, they are correct. But remember, we said we are always avoid including force that is not part of the motion. Okay, so we have our answer as some of us have responded in the pool. In the chat, we have A, C, D, A, B, C. Just 4 persons. A, B, D. A, B, C, D. Okay, so did we try to follow the method we just discussed? You kick the rock. The rock is now sliding down, sliding across, and it has moved 2 meters in front of you. So see, the force of gravity acting downward. The normal force, because the rock is on the ground. That is, remember when we describe normal force, we use the example of placing the book on the table, standing and resting your hand on the wall, on the ground. That's typically what this rock is experiencing. So we can describe or include that we have the contact force. So the answer to this is ABD. Okay. So had the frictional and the normal force. And also, friction, normal force, the gravitational pull, force of the weight on the object. Now, A, B, and D. If you look at C, force of the kick acting in the direction of motion. It's not one of the options. Yes, you kick the rock. So these are the kind of common error that is possible when describing, because you think that, okay, I applied the force, and so I should include the force of kick. The question is, which of these following are forces acting on you? You've kicked, now it's sliding. It's 2 meters in front of you before they now ask this. So in describing some of these forces, in identifying forces when there's a motion, some of the description of forces are implied in the question, some are given expressly. So it is that part of the implied force that tend to confuse us when we are describing, because we tend to say, okay, let's start from the very beginning. I kicked, so I exerted the force of kick. Well, that's not it. It's not part of it, okay? Because the rock is already in motion. Then we'll have air resistance acting opposite the direction of motion. So if the rock is rolling Are we saying that it's not coming in contact with a form of air resistance? Because every motion kind of have come in contact with air resistance. That is what will be confusing about the option E. But look at it, said air resistance acting opposite the direction of motion. Yes, drag always act opposite in direction of motion. But for this rock that has moved 2 meters in front of you, said sliding across the ground about 2 meters in front of you. So it's when we are describing that, we didn't include air resistance because we're no longer saying it is in continuous motion. You've kicked it, it has moved 2 meters. So you're describing the current state of the rock, not when it was in motion, okay? So those are how those two options could not be part of the option we picked. So let's look at the last part of our discourse today, which is having identified the forces, what do forces do? Why is it important that we study force? Okay. After the lab today, you see a more significant importance in the study of force because it informs mathematically the construction of so many things we make use of on
Like seat belts.
Yes, in our daily life. So without the understanding of force, we'll not be able to perfectly make some construction, which we'll see as applied to the construction of car or plane or whatever that will be moving human from point A to B. So when we talk about what do forces do, we want to really understand exactly how is force, understanding of force, important to us. How does an object move when we apply force to it? Does it just randomly move in the direction of force applied? So to answer that question of what do forces do, or how does object really move when we apply force to them? How do they act? We want to first start with a simple experiment, and then we call this experiment reproducible force. Reproducible force means we can reproduce it. It can, if you have a force and you have parameter defined, you can keep producing that kind of force over and over. So let's start with this very first experiment. Let's assume you have a rubber band, we've all seen rubber band. You put a rubber band on your finger, your 2 fingers as shown in this figure. You make a stretch, you measure that stretch, say up to 10 meters, and you call that stretch the standard length. At that stretch, you begin to feel a kind of force that tends to pull your 2 fingers together back to as if you're bringing it, that tension force on that rope or rubber band around your fingers. Okay, so this force tends to pull it back. But remember, we want to be able to say, okay, we can reproduce this kind of force anytime. So what we did was to use a ruler, measure the distance called the standard length, about 10 meters. Just stretch, you notice, with one rubber band on the finger. If you try to add another rubber band, as in this case, you tried it with one, you notice the force pulling it back when you did the standard stretch of about 10 meters. You now decided to add a second band, identical band. You made, because you already have the distance that you've put in the first case, measured out on a ruler called the standard length. You make another stretch to the point, that standard length as well. You will notice that this force you experienced in the first case is multiplied Okay, you notice that stronger pull, right? So when this was done, scientists went further to say, okay, there's limit to what we can do with our fingers. Let's try to reproduce this on another experiment. So we proceeded to, okay, let's try to do this again with a standard mass. So we now move to measuring the motion of 1 kg block, and we try to pull with a constant force. The stretch here, which covered the standard length, gave you something like a constant stretch, which when you decide to add more rubber band 2, 3, 4, 5, you will notice that the force will keep increasing. So as you're adding the number of band, it is multiplying also in force. So we'll have the standard force being multiplied every time you add the band. But in the second experiment, we discovered something striking. Okay, we use the same rubber band. We have a constant stretch, which we have identified to be 10 meters in the first case. We have several blocks of 1 kg mass. Okay, we pick one of the blocks of 1 kg mass, put it on a frictionless surface, okay, such that when we put the rubber band, we did the stretch, we pull it towards yourself. Try to maintain the constant stretch. That is, if you have chosen your standard length to be 10, that's from this distance to this, to be 10 meters, from when you put the block from point 1, 2, 3, as it proceeds towards yourself, maintain that stretch. Do not exceed the 10-meter stretch. You observe that from the moment you start pulling the first time, it becomes more easy, it just goes straight, as if you are experiencing a form of acceleration, right? This was tried several times and it gave the same results. It now led to certain conclusions, which we established here. That when you pull an object with constant force, it moves with a constant acceleration, okay? We pull an object with constant force, the same object, constant force, is going to move with constant acceleration. We notice that from when we start pulling, it accelerated. And we made the vector diagram of the motion. We see it started off, then we see it spaced out, showing that it is accelerating as represented in this. So our acceleration, something striking about the acceleration is constant. You see this, the arrow showing the same length, okay? So at constant interval, when this was observed, we noticed that acceleration is constant. So it is established that when you pull an object at a constant force, that object is going to move with constant acceleration. Remember, we pull this object on a frictionless surface, okay? So if you're doing a pull of an object and it does not obey this established fact, you know that a force from the contact is coming into play and changing certain things, but it's going to also accelerate at a constant speed, okay? If the force of friction can be overcome. Now, having understood this about the pull of an object with constant force. They went further to establish some other standard or scientific standards that we use today or apply in our everyday life or production chain in so many industries. What was done was, okay, I've done it for a block. I did for one block. What happens if I use the same rubber band? In the first case, I was increasing the rubber band, but what will happen if I increase the number of blocks? So they tried with the block, they increased the rubber band. For the one block, 1 kg block, we added 1 rubber band to 2 rubber band. We see that by the time we made the plot of acceleration against the force, which is the number of rubber band we add on that, we notice something, that the graph, we have the graph, positive graph, a straight line graph that was giving us, whenever we add 1 rubber band, we see the acceleration increase. We add another 1, acceleration goes to 2, acceleration goes to 3 according to the rubber band. So it was established from this experiment of trying out the rubber band with the way we did with our finger on the block, that acceleration is directly proportional to force. Okay, so we'll have on this slide 3 things to keep in mind at the end. We've seen the first one. In this case, and this is the second one. From that experiment, 1 kg block, we keep adding rubber band, we discovered that acceleration was moving faster and easier on that surface. So it was established here that acceleration is directly proportional to force. Now they changed the narrative by removing all the rubber band. Instead of adding more rubber band, we decided to add more blocks. So we used 1 rubber band on 2 blocks, constant stretch, then pull. We discovered something striking about the acceleration. In the first instant, we were experiencing an increase in acceleration. But when we removed all the rubber band and then started increasing instead of rubber band blocks, acceleration reduced. And it reduced in a defined pattern. Okay, so when we made the graph of acceleration versus number of blocks, we see this kind of graph. This kind of graph is always a graph of inverse proportionality. So it was observed that acceleration is inversely proportional to mass. Because when we used 1, we saw the acceleration of 1 block. When we increased the block, we saw the acceleration reduced to half. We made it 3, the acceleration reduced by 3. 4, acceleration reduced by 4. You see that the number of increase in 1 is leading to equivalent ratio of decrease on the other. So this relationship was established as inverse proportionality. So acceleration was now established to be inversely proportional to mass. And acceleration from the experiment is directly proportional to force. And from the experiment as well, we established that force when pulled, object when pulled with constant force will move at constant acceleration. So another striking thing that this inverse proportionality points out to us is that when you increase the mass, inertia increases. And what is inertia is this tendency to resist the change in velocity, whether you're speeding up or slowing down. Okay, So increase in mass leads to increase in inertia. So increase in mass leads to more resistance or change to resistance to change of velocity. So that is the sum of all what these two experiments has shown us. So let's advance quickly to understand the relationship that is implied as inverse proportionality. Okay, we have seen clearly from this diagram that when we increase by half, if there is an inverse relationship, it's going to decrease by the same ratio. But if it's a direct relationship, as you're increasing on one hand, the other hand is increasing as well. Increase in one would lead to increase, increase, increase like that. But this increase in one is leading to reduction on the other. So we say S is proportional to Y, and then this is the constant of proportionality. So express it normally as Y inversely proportional to S as shown here. This mathematical understanding made it easy for us to understand this relationship here as inverse proportionality sign, okay? So what actually is the implication of the statement inverse proportional relationship? So the implication is what we call the scaling. If you double S, you have Y. If you triple X, Y reduced by 3, and so on and so forth. So with this kind of relationship, we're able to come to a conclusion of what we call the ratio between two action or two quantities. Okay, so if we assume that for any ratio value of X, say X1 and X2, we have Y1, constant of proportionality, and Y2, can we relate these two? These two events can actually be related. So what we did is to divide Y1 equation by Y2 to get the ratio. So dividing this by this took care of A, took care of A, and then we'll have the final to be Y1 over Y2 is the inverse of the other, which is S2 over Y1. Okay, so this is actually the equation of, or implication of that equation of inverse proportionality, which we will see in the next example. Okay. So let's quickly take the.
I just have a question. In that like formula up there, is A just acceleration?
This A here, is this the A
like
in this case? No, A is the proportionality constant or constant of
okay.
proportionality. Okay. So that's what this A is. So it canceled out to give us this relationship. So let's see this example. When a rubber band is stretched to pull a 1 kg block with a constant force, the acceleration of the block is measured to be 3 meters per second. When a block with unknown mass is pulled with the same, not the word, the same rubber band using the same force, its acceleration is 5 meters per second. What is the mass of the unknown block? Now, if you look at this question without applying any formula to it, it should tell you if from the acceleration is the mass increasing or reducing. From the inverse proportionality relationship. Because if it was a direct proportionality relationship, an increase in one will automatically lead to the increase in the other. But in this case, it is the same, look at it, the same rubber band, the same force, pulling the object, but there was an increase in acceleration. So that means the question is talking about a mass change, okay, or change in mass of the object. So the question is now, what is the mass of the unknown block? So analyzing that, when you get your answer, you should be able to tell if you're on the right track or on the wrong track, if it applies or obeys the established principles that we have looked at, okay? So we use the ratio relationship. This is one, sorry. Y1, Y2 will give you S2, S1. So we used understanding of our ratio relationship or ratio reasoning to solve this problem. Okay, so acceleration and mass. So A1 over A2 equal to M2 over M1. That's what we applied here. Okay, let me write it in a clearer way. A1 over A2 equal to M1 over M2. A1, A2 is given. M1, sorry, inverse proportionality, M2 over M1. Okay, so M2 is what we're looking for. We have the M1, we just made M, that's the parameter we're looking for, the subject of formula to get the final answer. We see that the final answer actually gave us a mass that is less than the first mass, which agrees with the inverse proportionality ratio. So if the mass of an object is reduced, we expect the acceleration to do what? Increase. An increase in one will lead to reduction on the other. So if you increase the mass, acceleration reduces. Okay, so this agree perfectly well with that conclusion from the experiment. Okay, so let's take the squeeze quickly. Two rubber bands stretched to a standard length. A standard length can be the length you defined, okay? All right, like in our experiment, we defined 10 meters to be a standard length. The standard length is defined as the reproducible length or something that can be replicated. So a standard length, the rubber band stretched to a standard length cause an object to accelerate 2 meters per second. Now suppose another object with twice the mass of the first one, twice the mass, is pulled with 4. We're pulling with 2, we increase the mass and we increase the force, about the same proportion of increase. The question is, what is the acceleration of the second object? So suppose another object with twice the mass is pulled with 4 rubber bands stretched to the same standard length. What would be? Yeah. Reading the question, you automatically knows that it's going to be, it's like saying 1/2 and then, yeah, 1/2, you now say something like 2/4. You're still within 1/12, 5/10. You're still talking about half. Okay. So the answer is this 2. Can't find my pen anymore. Okay. So the answer remains 2. All right. So by next class, we'll be looking at the second law of Newton and the third law, and we'll be done with the chapter 4. If anybody has a reason not to be able to take the midterm test in 2 weeks' time, I'd like to have your reason beforehand so that it will help me define the date we're going to put this test. I'm looking at putting it on a Wednesday or a Thursday, a Friday. Well, we will use our lab. No, yeah, we'll use our next week lab to do a kind of revision, a recap of all we've done and what to expect. Then we'll take the test the upper week. And if you have any reason or an excuse that will keep you away, I'd like to receive that before the end of next week. Okay. So does anyone have question?
Wait, so which day did you say the midterm was on then? Sorry. I just want to write it down.
Okay, I'm looking at the upper week. The next week is Thanksgiving. The week after Thanksgiving, 13th or 15th. Once the exact date is decided, I'll post it as announcement to all of us. Okay. And I confirmed the November 8th to 12th date. Yes, it's lecture free. We'll not be having any class those days. Okay. So we'll forget what the schedule say. We'll have slight modification on our lecture schedule, which will be relayed to us as we move on.
All right, thank you.
Thank you. Does anyone have comment, question about today's class or previous classes? Okay. If you don't have now, maybe when you start studying, feel free to send me email, contact me. If we don't see in person, we can arrange to meet on Zoom. Okay. All right. Thank you. See you in lab today. For those of you with Wednesday lab. All right. Bye-bye.